All right, welcome back to Mr. G's EV Hangout. It's really more about the DIY electric vehicle conversion community. We just exchange ideas. An idea we came across tonight was, can you get the CAD file of a Tesla drive unit? And if you do, can you 3D print it? And if you 3D print it, or can you get it made in foam, and then you could test fit your Tesla drive unit into the frame rails to see if it fits. So we did a little experiment with the help of Richard from the EV Riders and Kevin, and we downloaded a Tesla drive unit. So Richard, what project are you going to use this for?
Well, it's all super secret source, but a small sports car. We're looking to replace the rear differential with Tesla drive unit, and it may be too small to fit. May have to cut the rails.
Okay.
Yeah.
That's pretty
What about
cool.
European Miata?
Yeah, something that size maybe.
Okay. That's cool.
So it's a vehicle with independent rear suspension and a differential, with a drive shaft. And the idea would be to get rid of the differential, put the Tesla drive unit in there, make custom drive shafts up. So the question is, will the drive unit fit inside that?
Okay.
That
now,
area, which is everybody, I guess, thinking of doing this.
You should know that last week on my other podcast, the Shop Class podcast, we interviewed Brandon from Amp Revolt, which is in Lancaster, Pennsylvania. And he has a drive unit that they sell you the modification for. They lock one side of the differential, and they sell you the drive shaft adapter, the yoke, and you turn the drive unit 90 degrees, and you go longitudinal.
Yeah,
So
so
that's
you use
an
the
option.
space for the motor and the transmission, which is more space, and leave the rear suspension all original. Yeah, that's interesting. But
and he's a really good dude. He also he taught with me for a while, and so he's pretty knowledgeable. Here it is, and I could show you what it looks like. It's an option, and the whole interview's on the Shop Class podcast. Let's see, motor accessories. His website doesn't go straight to it, so he sells you this thing here. I think this is the drive shaft adapter kit, and I think he's got a video. Yeah, he's got a video. There you go. I don't know if you can see that. It's underneath the vehicle, and this is really for heavy duty stuff where like if you have a really heavy duty 4-wheel drive, or like let's say a rear wheel drive, but you have a large differential live axle and you don't want to change it because you want to keep the integrity of that robust, like let's say a delivery truck or something like that. Not that the drive unit can't do it, but you'd have to build some sort of suspension system to do the half shafts. Well, in this case, you don't have to change anything. So it's an option.
And the advantage to what Richard's trying to do is take this thing, use the built-in differential, and there's no additional losses, and take all the front space, the front of this car, which is pretty small, and put batteries up there instead. So use where the engine and transmission is and stuff out with batteries, and use this Tesla drive unit, which has a differential built into it, and put that in the back.
Nice.
But this is a way to go too. Yeah, in the case where you want to preserve the original drivetrain. A good reason for that, yes, it's 4-wheel drive, because then you put this right into the transfer case and you still you've maintained your 4-wheel drive.
Yeah. All right. So yeah. So the format of the show, we were discussing that as well. The format of the show is this EV community show is that we talk about. We highlight people's people that come in, their projects, and then we go to like a Q&A session. One of the projects that Richard was bringing up is really he had questions. So we went right into the questions, and we came up with there's a couple of things you could do for this situation. One of the things is if you don't have the drive unit, you might want to mock it up on CAD. And one of the CADs that I suggested was Onshape. Onshape is like a free software, but it's not garbage. It's real. It was designed by the same people that did SolidWorks. So that's pretty cool. And, you know, I have some teaching videos online if someone wanted to learn how to use Onshape. It's pretty straightforward. And then we got to talk about like like a foam mock-up engine, if we could 3D print it the same way they used to sell, or they still do. They sell these. I mean, it's so funny. They sell you a foam or plastic engine for like $600. You know.
Yeah, because when you're trying to fit these in a car and you're trying to see if you have enough space, you're off by an inch or two. You're trying to route exhaust pipes and things like that. It's way easier to do with a 20-pound plastic engine than a 600-pound iron engine.
Yeah, exactly.
You got to keep pulling this thing in and out, the clearance frame members and things like that, and route exhaust way easier with something that's light and easy. Same deal with the EV stuff.
Gentlemen,
yeah, go ahead.
yeah, we could do this with two-part foam. You know, have you guys ever worked with two-part foam? Make a mold. We could make a mold at EV West with their Tesla Model 3 drive unit, and then cast our own foam model.
Perfect.
That stuff is easy to work with.
Yeah, it's making the mold is going to be a little tricky, but yeah, you can use vacuum forming. Is that what it's called?
Oh yeah, vacuum forming would be pretty good
to make the
and
mold.
Just make it in halves. They do it in halves. You know, you just make up a little box, and set the drive unit in there and fill it up to the halfway mark with this two-part foam. Trim it all off. Of course, the drive unit is covered with oil, so it pops out real easy. And then flip it over and do it again on the other side. Now we've got a mold. And then we line it with wax paper or grease or whatever, and do this whole thing again with build the model. Top
I
toolmakers.
agree. Yeah, I agree. And maybe that could be done at the EVLC as a project layout class. You know, like how do you size the parts for your project? That would be a pretty good class, because that goes into metal fabrication and engineering and mechanics. And know, Sarah is not that far. She's in California, and Kevin's close by, and so is Talik, and so is Richard. Maybe this is something that we could do. And Tom, if you know how to do it, we could all work together, you know. Here's an example that I had to deal with when I was working on a Chevy K2500. What we did was we mocked it up, and we would we would mock it up in CAD, just like what you're talking about. This is the kids mocking it up. This one's not quite right, but the drawing is there and all the measurements. We had to take our measurements. And so yeah, like the fitting, like layout. This some people call this an engineering packaging. Like, where are you going to put everything, basically? You know, it's not easy.
Yeah.
And that's not something we cover, I think, in EV 101. I mean, that would be really good, actually, you know. So yeah, I agree with that. That's a pretty cool one. And then
it's a place where a lot of people get stuck. You know, you bought the parts, now you're trying to fit them in your little car. How do you do it? And you get tired of, you know, pulling motors in and out trying to fit things in. I'm getting tired of pulling batteries in and out. Same thing could be done with batteries. You know, these batteries are big and heavy and bulky, and I'm trying to get them to fit in my frame.
Yeah.
Polystyrene models would be cool.
Yeah.
We do that a lot on boats. We make mock-ups. And by the way, Victron had those battery dummies that we talked about Victron last week. Yeah.
They have dummies.
Oh,
That are
right, they had. Oh, because it's a. Yeah, of course, because they're heavy. So they had mock-ups for you.
Yeah. And this is very common in the boat world. It's the same thing with automobiles. Nothing is plumb and square. You've got all these weird shapes, and you got to make some cardboard mock-ups with Scotch tape and scissors and all that good stuff, just to fit stuff into compound curve shapes. And so mocking up is something we do a lot of.
I agree. And then showing some in the basic CAD, but also hands-on skills. So you might not always have access to CAD or want to work in CAD. So you might want to mock it up in, just in cardboard. I'm just looking I have a mock-up engine in here somewhere. I'm looking through my photos. Pretty cool topic. Even the adapter plate, if you don't have an adapter plate, you can just mock it up in, plywood if you had to.
totally. And then there's these services like Send Cut Send, where you then send them the CAD model of this, and they'll send you back this thing made out of metal, exact, with all the holes drilled and everything.
100%.
And don't forget, we have that machine at Michael's that does the bell housings and sends out the PDF file for it to be, turned out on a lathe or whatever. So we're already doing this.
Yeah. Yeah, we just don't serve the mock-up side of it. They, if your company, they go straight to the end product. Actually, I'll tell you something funny. Clearly, you're going to buy a coupler if you had, let's say, the Net Gain or AC50, but believe it or not, one of my students came up with an idea. Do you guys see this photo? This is a very important photo right here. This is the end of the engine. This is the back by the transmission. This is where the transmission meets up. Notice something. That looks like the end of a coupler. What we realize is all you have to do is take the drive shaft out of the engine and cut off the end of the crankshaft. Sorry, the end of the crankshaft. I'm going to show you a photo of that. The end of the crankshaft is a coupler. All you got to do is put it on a lathe. Here's the mock-up in a 3D printed example. And I couldn't believe it, but believe it, of course you're going to buy the coupler, right? Because Canadian electric vehicle, they have them, they're available, but here's like a mock-up of like our 3D printed one, and that's not going to last, obviously. But we then went and cut the end off the crankshaft. It's like a bit extreme, but just the idea that you have all the resources you need on the old vehicle. That's got a lot of dimensions. You might want to take note of those dimensions before you tear apart the car and stuff like that. Yeah, so these are kind of some of the things that we come across in when you're doing these mock-ups. Actually, we got crazy. We were at a college and we didn't have time. Like if you're working in 2 locations at once, we made an engine stand for the whole thing. So this was our CAD drawing, but we put the motor and the trans on a stand because the truck was not available at the time. And so that's an option.
Guys,
anyway,
I have to sign off. I'm sorry. Keep going without me. I'll see you next week.
Okay, thank you so much, Kev. See you later.
Thanks, sir.
Okay, so in the interest of time, we should probably go to the next project and questions, and I think that's we're going to jump over to Sarah. And Sarah's working on a project. Maybe Sarah, you want to give us like a status update? If it's secretive, that's okay. If you want to just give us your question, that's fine. Yeah, tell us what you think.
Status update is got the motor to spin, and it's a 1987 Suzuki Samurai with the Type 9 and 5 Tesla batteries. Yeah, we got the motor to spin, and we have 2 chargers. We got those to charge. But now my BMS is telling me that I have 1 cell that's overcharging. And so it shuts.
Oh, really?
Yeah. Cell 25 in HVC. And this whole like using PuTTY to communicate and program all this stuff is new to me. So that's like, I'm like reading the instruction manual, but I have no history with it prior to this. So that's what my question is. What's been your experience with BMS and, you know, a cell overcharging, and how do you like troubleshoot that?
Okay, so let me just jump in real layman's term. We had this issue over the summer with the bus, where when you say cell, it's actually 74 in parallel on a Tesla, a Tesla module, and so it's 6 series 74 in parallel. I'm pretty sure. And then when we had some strange voltages, and then when we went to go charge it, it charged up, and it went from like, I don't remember, around 3 volts straight up to no, not 3 volts, maybe 3.5, straight up to 4.2, and shut off the charger within a minute, and we could video that. So it turns out that a lot of the cells were low capacity, either disconnected or destroyed. It was really hard to prove that from a physical part of view, because we had to, even when you check the voltages, it seemed okay, and we couldn't figure out which cells, because there was none of the fuses were blown from what we could see, but there might be an internal fuse that was disconnected, because I've heard some of the 18650s have fuses not just on the outside, the little fusible link, but also on the inside. So that's my overview, that you might have a low capacity like bank. What is Richard, what do you think of this situation? And maybe you could help with the PuTTY.
Okay. Yeah. Can you hear me?
Yeah.
Yeah.
Yep.
So can you tell us a little more about your cells? Where did they come from? What's their provenance?
Let's see. They say EVPS on them. I don't know who.
Did you buy them all at once from the same vendor, same source?
Yes, the people who supplied the motor, all the parts, controller, everything, supplied these 5 modules, and guaranteed that they were good. And when we first started, they were good and balanced.
Well, wait. Let me interrupt for just a second. Something I learned over the summer is good, quote unquote. If the voltage is good, that is a false sense of security. Yeah. And I had to learn the hard way. The voltage might be close to balance, but if you have low capacity, which is a confusing term, if you have 74 cells, but you're only actually reading 2 of them, they might give you the correct voltage, but then when you go charge them, they're going to charge up faster than 74. I don't know if you follow.
Yeah.
It's very difficult to explain this stuff.
Have you heard of the term
Yeah.
nominal voltage? Right, for a particular chemistry, let's say it's 3.7 volts. So a cell can be at 3.7 volts, whether it's at 90% capacity or at 20% capacity. It's only at the very end, when it's fully charged, does it start rising above that? Or at the very end, when it's fully discharged, does it start going below that? So you could have 72 cells that all read 3.7 volts, and you could have some at 20% and some at 90%. But that's why I was asking why, the provenance of the cells, if they all came together, did they come from the same? Are these being recycled from another vehicle, or are they brand new?
I think it was probably a wrecked Tesla that they've been salvaged from.
Okay.
Yeah.
All right. So if they all came from the same wrecked Tesla or any modern EV, they should all be pretty much at the same state of charge. Okay, and they should have probably a similar capacity. Depending on how many. Do you know how many miles were on the car?
No, we don't.
Okay.
We could ask the supplier if they know.
Yeah, it's always a good idea when you're looking at batteries,
I think,
is to ask, how many miles were on the car to give you a rough idea what to expect. But if they all came out of the same wrecked car, there's a good chance they should all be pretty close. But then what's happened to the cells since? Like, did someone take one module from a Tesla and use it for something? That might have taken its, some energy out of it. And so it's out of balance with others, even though the voltage looks about the same. So the only real way, before you put any cells in a car, I would suggest, is you need to do a capacity check on them.
Okay.
Which means, draining all the energy out of them, and then, balancing them roughly at the bottom. You may not need to do that. Actually, just draw them down to a low voltage and then charge them up, whilst counting coulombs, as they say, or counting amps or amp hours. Amp hours is the big term. And then you should be able to find out, what the cell capacity was when they were new, and they could be close to that, or 90% of that, or maybe 80% of that, but you won't know unless you actually do a test. And so it'd be very good to know, like, have it written on every one of your cells what its capacity is. And because a battery pack is a chain where it's only as good as the weakest link, it's the one with the least capacity is what your pack capacity is. The others just are working less hard. So whenever you have used cells, it should be on your project plan to capacity check them.
How would you drain them?
There's all kinds of different ways. But yeah, I mean, there are testers out there that automate this for radio control vehicles, for instance. These just have a lot more capacity, but you can use tools like that. At our club, we have something called we have this big box that has a whole bunch of resistors from diesel electric trains, and which are very low value resistance. And so you put a pack against those, and those get really hot, and they burn several tens of amps or hundreds of amps are pulled out of the pack. And you need to have your BMS connected so that you can detect when your weakest cell, or the one, not necessarily your weakest cell, the one with the least capacity, least energy in it, when that one starts to drop off at the bottom of the curve, you need to disconnect your load or disconnect that cell and work on all the others. So it's actually a long, tedious process to do this with used cells, but it's worthwhile doing because you don't want to have to do it in your car 3 months down the road or whatever. It's just know what the capacity of your weakest cell is.
Luckily, I have all these. I've done all this on the bench. None of it's in the car.
Exactly.
So
That's
I
a good
basically-
move.
Would you like to see?
Sure. You're about
Yeah.
to see our delta here. We had quite the spread on.
I'm trying
this
to, Talik, I'm trying to find the video. Do you think you know where the video is? Because it shows us charging and then the BMS shut it off.
Kevin had a video.
Oh,
Yeah.
that's right. He has it on his like channel.
Yeah, he had. I don't know if it's unlisted, but he put that on YouTube to send to the class the next day.
Okay, I'm gonna try and find it.
Oh, Kevin's huge resistor. Is that what you're talking about?
Well, so there's two different things going on. So yes, there is a resistor, sort of setup that I think Richard's talking about that's at the EVLC now. And maybe they have two of them, but that's discharging. And it also, you should not do this without the BMS hooked up. So just keep that thing hooked up. Now, but what we did was we charged in the summer because we were having issues where the voltage was strange. There was a runaway a little bit, and like the voltages were creeping apart from each other. And then when we went to charge, the BMS shut it down within a minute. So then when we went to go look at these cells, nothing looked damaged. But that's the scary part. And it came from, this is why Richard asked this question. It actually came from a wrecked Tesla, but then was installed in a Jeep project. And then after it was installed in the Jeep project, it was then put on a shelf at EVLC, and all they did was test the voltage. So then it's like a false sense of like, oh, these batteries are all in check. Now, I want to just separate two different concepts here. One is that what I'm talking about is that you read it and the voltage seems okay, and that is supposed to be 74p, but it's not. It might be 2p because the others have been disconnected somehow, or they're dead or whatever. What Richard's talking about is another false that can throw you off, which is that the voltage doesn't move that much from the middle of the capacity. It's only at the end where it goes from like 3.8 to like 4.2. When I don't know if it's 80% to 100, but when you get to that top or bottom, that's when they go up or they fall off a cliff. They really don't say much in the middle. It's kind of like a person. You're sitting there and you look normal, but if I asked you to run like 5 miles, like emergency run 5 miles, then we'll find out if you're in shape or not. Like we'll find out real quick. You look normal, but you might not be ready for battle. Like I don't know how else to describe it. It's
also like a fuel gauge that gets stuck in the middle, and then you're running it out, but all of a sudden the fuel gauge goes, oh.
Yeah. Richard, did I do a good job? Oh, I muted you because there was some feedback. So unmute yourself and tell me what you thought of that description.
Yeah, no, that was good. And just to be on a positive note here, there may be nothing wrong with your cells. You just may have some that are more discharged than others. So you need to, like Ron was saying, probably the easiest thing to do, first of all, is to charge them until they're all at the top, like 4.1 volts, thereabouts.
Yeah.
Okay. I mean, 4.15 or 4.2 or whatever, just get them all at the same level at the top, because that's easy to do. You can just keep charging until the BMS sees the highest one. Mm-hmm. And there's various techniques to bring everybody into the same place. But if you bring them all up to 4.1 volts or 4.15, whatever, then you can say these guys are actually at a similar state of charge. They're all at 90% approximately. And then the capacity check, though, is to then draw the same amount of energy out of all those cells, put them together in a pack, and draw the energy out of them one way or another. So resistor is one way. There are some interesting other techniques that I don't know if I should describe in this forum, where you can, use the energy efficiently and put it somewhere else. But anyway, draw the energy out of the pack. And at the same time, very important, you have to calculate the amp hours. So either you have a BMS that has a current sensor that's tracking this for you. It's just looking at current over time. You pull 100 amps out of the pack for an hour. That's 100 amp hours out of the pack, right? So you can even do it manually by just keeping track of how much current's coming out over time. But ideally, you have something that's tracking that. And then, when it gets towards the bottom, one cell out of all of those is going to go low first. Okay. And then you just make a note of how many amp hours you are at that point. And then it starts getting tedious because you kind of have to give that guy a rest, but the other ones may have more capacity. So you could keep working, you could take it out of the pack and then work on the others. And that's a really tedious way to get to know what all of your capacities are, but you could just quickly the first cell that starts going low, you say, okay, that's my pack capacity because that's my weakest link. I'm not planning on changing out any of my modules, but I now know what my pack capacity is. And then you can charge it back up again, make sure everybody's sort of balanced at the top. And then in your BMS or your VCU or whatever it is that you're using to manage your system, you just configure that and say, that's my known good amp hour capacity. Okay. I mean, there's some variations, like if you're in the vehicle and you're driving hard with a low battery, they're going to die quicker, right? But in general, just getting an idea of what that number is, what the capacity is of that pack you actually have there. And if when you're discharging, somebody goes low very early, and you're expecting, say 100 amp hours, but somebody starts going really low after only pulling 50 out of it, then that maybe is a suspect. And you might want to try replacing that with another, but then you have to charge everybody up again, then do the discharge test again. But if it's within 90% of what the rated amp hour capacity of that pack should be, and you probably have a good pack. And you can get, if you've got ADD, you can work on figuring out what every last cell is. But the quick and dirty is to get them all charged up to around about the same full level, and then discharge them. And let's say that first one that falls off the curve, that's where you say that my pack has this much amp hours in it. Okay. And you can multiply that by voltage for kilowatt hours and so on.
Okay. When we first got the chargers to work, they charged all the way up to 4.1, almost 4.2.
Mm-hmm.
No faults or anything. But then I did some work on the CAN. I worked on some other stuff. I didn't touch the BMS or the batteries. But then once I started trying to charge again was when this started to happen.
So what's happening now? When you charge, one of the cells is higher than the others?
But it doesn't actually, on the show cells, on the BMS, MCU, it doesn't actually read higher than the others, except all of a sudden the error says C25 in HVC. And it shuts the charging off, and they've all got about 4.004 volts. So
one of them is at 4.2, whatever the cutoff is set to?
No, none of them are at 4.2.
So why did the charger shut off, or the BMS shut it down? What was the error?
I put it in the chat. It's 1/C25
in HVC, high voltage
cutoff.
Which BMS is this? The dilithium one?
Yes.
Okay. I have played with that in the past.
You can change the settings.
Yeah, the supplier went and did TeamViewer and helped us set up all this.
Okay.
Yeah. So I'm learning through.
Yeah, it has a little serial terminal on it, right? With that little console, and you can get it to list out its configuration.
Yeah.
That would be a good thing to pop in the chat if you had that sometime, or to the group, so we can see what the settings are. But so HVC has a setting for whatever that voltage is, which should be 4.2 or 4.15.
Yeah, we've set it at 4.2. Yep.
4.2, which, by the way, is the very tippy top.
Should probably not be.
Yeah, I would bring that down a little bit, because you've got nowhere to go other than over voltage from there. So you've only got 5% of charge or 5% of capacity or something up there. So be conservative and do 4.1 or 4.15. So you don't have a cell that's on the hairy edge. It gives you more time to react. And if they're all balanced at 4.1 or 4.15, I would suggest that but rather than 4.2, at least initially. So you've got some room for error. And you're always going to get one cell that causes you to stop charging because it's in high voltage. It's not necessarily a problem. He's just the first one to get there.
That's what I was wondering, because right after it says 1C 25 okay.
Yeah.
Like
so after you stop charging, when you're pushing current into the cells and they're near the top, the one that's the weakest, or the one that's most charged, not necessarily weak, the one that's most charged, its voltage is going to climb up more rapidly than the others because it's really close to being totally full, right? And so every time you charge a pack, one cell or the other, and it's usually the same one in every pack, is going to be the one that gets up there first. And then you stop charging, and then you look at the cell voltages a few seconds or minutes later, and they're all identical again. So there's not necessarily anything wrong with that.
Okay, so that's kind of what's happening.
Yeah, and I wouldn't say you have a problem yet. So
I have I don't mean to interrupt, but I have a video here of a real problem.
Oh yeah.
Okay.
So this is what happened in the summertime. We were charging. We had some voltages that were kind of like not close together, and you could see like C3 is like 3.6212, and then there's also like C10 is like 3.566. So they're not close. And then when we charged it, one of the cells went up so quickly that it shut off the BMS or charger within a minute. So here's the video. The video is only 2 minutes long, and I'll show you what happened here. We can actually maybe put some closed caption on it. There we go. Here we go. Okay.
We've got potentially another bad module. Everything is fairly well balanced right now. As you can see, this is a list of all of the current cells. You got to get ready to slap the card again. Somebody's got to sit there.
yeah, I got it.
Now we're going to turn the charger back on. This is happening at higher currents. Specifically, you slapped it?
I'll wait till you get in, right?
No, slap it. What's wrong with me?
And that's just setting up the charger on the wall. But here we're gonna get to the to the putty terminal in a minute here. Get in the bottom first.
Okay.
Not happening. You need to push it in.
In Sarah's case, she's got a matched pack. It may not be indicating a problem.
See, this is still up.
All right.
So do that capacity check.
That was literally the connector. Sorry. Okay, here we go.
I am putts. Now do a show cells, please.
Charging.
Mark.
Get closer.
Now it says cell 30.
Okay, cell 31, 3.75. You guys see that? That's bad news. Look at all the other cells.
Are these
really
LiPo
bad.
cells? These are LiPo, right? Not.
This is
LM.
Tesla module, and they were bad.
These are Model S 18650s.
Model S.
Yep.
So fully charged, they are 4.2 or 4.1, right?
No,
So you're
I
nowhere
didn't
near
finish the
fully charging
video.
them.
I didn't finish charging. I'm just showing you how fast this happens. Watch the refresh. It's going to be at like 3.8, 3.9, boom, and then it shuts off the charger. So here we
All
go.
the rest of them stay kind of nominal.
Yeah.
31
So
that we
that could
think
be a bad
is the issue.
cell, or
Do a
it
show
could just
again,
be a
please.
cell that is being discharged.
What's that?
That could be a bad cell, most likely, but it could also be just that the cell was discharged separately to all the others, and so it's getting close to being full before all the others do. See what I mean?
Discharged? I mean, it went from 3.6 all the way up to 4.2 in a half a minute.
Yeah.
They started in a similar voltage range, but then it accelerated faster than the other ones.
Yeah. Well, yeah, in this case, that probably is a bad cell. It's basically showing that it's full before all the others were. And if it was exposed to the same energy draw and it's being charged and discharged with everybody else, and suddenly it's behaving differently, well, then that's a bad cell. But in Sarah's case, we haven't got a characterized pack yet. We just, you know, we've got these modules that all came out of the same car. After charging them, you know, you have one cell that causes the charger to stop. That's always the case. And they're all looking about the same. So really the thing to do is to actually do a capacity check to characterize what kind of pack you have.
100%, Richard, you're 100% right. I was just showing Sarah a nightmare scenario going from around 3.6 all the way to 4.2, shutting off the charger in a half a minute. And we already installed the pack in the truck.
And this was also after trying to trickle. This was like after trying to set it on the BMS overnight, right?
This was after balancing it in parallel on the bench and then trickle charging it to get closer over a couple of days. This was after a lot of work, in and out, swapping, you know. So here, watch this happen. Ready? Here we go.
It's up to
There, look at the refresh. I don't know if you could see that. That cell 31 is up to 3.92992, and the rest of the cells are in the 3.6, 3.7 area, and some at 3.5.
Now, had you characterized this pack before you did all this, or is this the first time you're really trying to work it, right?
That's the magic question right there for the summer.
Yeah. Honestly, this is what I advise people. You get a set from a supplier. They really should be stress test. I think voltage is not an indication of the health of the pack. Would you agree with that, Richard?
No, for sure. That's a rough indication of how charged you are. You're either in the no man land, you know, between 90% and 80%. It's only when it's starting to go up or it's starting to go down that you know that you're nearly full or you're nearly empty. But if this pack started with everybody nearly full, and then you drove it around a little while, and then you went to charge it up again, and this cell's behaving like that, that's clearly a bad cell. Right? If you hadn't taken them all the way down.
This is how we received them.
Yeah.
Also, we didn't have the time with the project to try to take apart the module and try to like test each. You have to basically treat a module as the replaceable unit. But individual cells within a module can be bad, right? Especially if it's come from a wrecked car or you don't know what's happened to it. But yeah, if you find a bad cell in a module, there's not much you can do about it other than replace the entire module.
Right, because they're kind of like glued in.
Yeah.
So, Sarah, does this jive? Does it make sense to you?
Yeah. I wish I could show you my screenshot of the history, because it shows the watt hours and the voltage and the current. Yeah, just to reiterate what Richard's saying, I'm not saying you have a bad module. I'm just showing you what happened to us last summer. And I learned my lesson that you really do need to know the capacity, or at least discharge, or not all the way, but discharge a little bit or charge a little bit and just see how they act. Voltage is not really
it's not going to be a good indicator. And if you watch the last 30 seconds of this video, you'll see it rises up to 4.2 and shuts off the charger. So here we go.
So the only way to,
3.92.
do
Oh, go ahead. Sorry.
to refresh it, it won't show it in real time. Is there no way to show it like?
No, you have to refresh it. I forget the word command. Richard probably knows it.
Shows.
Yeah, with that screen, you have to keep typing it in.
Okay.
Or you may be able to get your terminal server, whether it's PuTTY or something like that, to repeatedly send the show cells if you're using that screen. But then if you do what Kevin's done and you've got some coding chops and a CAN bus, like Kevin is constantly reading these cell voltages and displaying them on a screen. So this is just the simple tool that comes with the dilithium BMS, right? But with just this, again, if you automate the SH cells command to send that every couple of seconds, that might be good enough. But certainly when you're first charging your new pack, it is a good idea to keep an eye on this, because what you're doing is you're characterizing the pack. You're figuring out, which are these modules, what's the capacity, are they good? And if your supplier actually gave you a report that tells you what the capacity was, that they did a capacity check themselves, that's great. But I'm not sure that every supplier out there does that. And even if they do provide you with a report, it's like, well, how much do you trust it? Probably quite a bit, right? If it's a good vendor. But you probably want to do your own test, because you don't know what's happened to the cells in the meantime. Someone could have dropped a wrench across the terminals. Okay. So these things happen, especially in our amateur world. And so doing the test yourself, you have your own personal confidence of what's going on with all these different modules is a good thing to do before you invest a lot of time putting it in a part of the vehicle where it'd be very hard to get out.
This also, Ron, not that this is a main cause, but do you remember that one of the BMSs also go bad throughout this process?
Yeah, actually, these cells might have killed the BMS, or the BMS. I don't think the BMS killed these cells. The modules came out of a wrecked or given up on project, like a DIY project. Unclear history. It just showed up.
Yeah.
And they salvaged it out. That's not straight from a Tesla. From a Tesla, they are protected. They are managed. It's some of the best quality stuff you can come across. So that's why this was a shock to everyone involved in the bus project, because no one believed that this was what was going on, but it absolutely was. So if you watch the last 30 seconds of this, you'll see it run away and shut off the charger. Here we go.
We're charging 15 amps.
There's the next refresh, and now we're up at 4 volts on cell 31 and still down at C8. I don't know if that's the lowest cell, but C8 is like 3.5. So this is like a runaway. This is like, they are completely different in their capacity. Go ahead, Richard.
Well, another point he's saying is charging at 15 amps. Okay. What is the amp hour capacity of these modules?
Oh, these are, they're 5 kilowatt hour with, yeah, but at the amp hour capacity is a much more, kilowatt hours is voltage times amps, right? So you're a bit further away from the key number, which is amp hours. That's what you calculate when you discharge and recharge it. You don't really care what the voltage is. You're just looking for the capacity. And so if you have 150 amp hour cells, and you're charging them at 15 amps, then you are pushing in a tenth of their capacity, right? So the more current you throw into a battery, the faster its voltage is going to rise. So that's also a factor. You should be possibly lowering the current when you're near the top for a particular system, and some BMS do that. This was the thing. As you can see, the nominal of this pack was it was around 3.6, the nominal when we started. This was literally just trying to charge the pack
after we had supposedly balanced it overnight and a day or so. So, you know, we were trying to do things, you know, relatively simple, and, you know, in fact, it might even be doing 12 amps at some point. Well, it says 15 there, but I think we backed off the amps at one point, and it, you know, yeah.
But 15 amps across 6 modules. Isn't that pretty
Well,
low?
every cell in there is seeing 15 amps. So if you're a cell that is at full capacity and you're putting 15 amps into it, it's going to rise its voltage very quickly.
But
Okay?
it wasn't at full capacity. According to these voltages, it was like halfway or low.
Well, okay, you're at 3.6, 3.7. That's your nominal, right? Again, at that voltage, you have no idea what its capacity is. It's only when you get up above 4.0, 4.1, can you say that cell is nearly full. And so what you have here is you have a cell that's acting like it's full, but it's acting like it's full way ahead of all the other cells that supposedly it was at the same state of charge with. So you're probably right, there's a bad cell here behaving this way. But if you've never balanced all of these cells together, and again, these are Tesla modules, so you know, within a module, they should all be the same, right? They've all experienced the same thing in their lives. When you're building a pack out of individual cells, you don't know what any of them are, right? So I agree. Because this is a Tesla module and it's one cell within a module that's acting this way, you probably have a bad cell in that module. But if you're starting from scratch, every cell is an individual.
I see what you're saying, that in this case, it's a bad cell, but it's similar in characterization, or however you want to put it, that if you were close, I mean, these voltages are not close, but if you were close to the point where it ramps up, it would be hard to tell whether your pack was whether you had a bad cell or not. Is that what you're saying?
Yeah, because one cell is always going to go up before all the others, right?
Yeah, but this is a big spread, no?
It's a big spread. Yeah.
Well, it was also a big spread after we put it under charge. After it was sitting on the BMS, the delta between these cells was a lot closer before we started to try to charge it with the level 2 charger.
Yeah, when you stop charging them, the voltages will drop at that high cell, and they'll all look like they're close together again. And you start charging, and it'll pop up. It's like whack-a-mole. Yeah. And then the BMS will start trying to pull some charge out of that high cell, right, to bring its voltage down, like bleeding it off into a little resistor in the BMS.
Yeah.
And so that guy gets brought down a little bit, and then you can put a bit more charge into the other cells, and that's top balancing. Yeah, when all the cells are at 4.1 volts. And you're top balanced. And then you discharge the pack until they start dropping off the other end, and you say that's your amp hour capacity right there. And then when you charge it up again, they should all get to that 4.1 roughly at the same time. Yeah. If you get this situation here where one cell goes reaching up to 4.1 where the others are all sitting at 3.6, then you have a bad cell, right? Its capacity is way less than all the others in that particular pack or that module. Yeah,
and we only saw that when we actually put it under charge, because again, when it was after the BMS, there was probably 3.5 to 3.6 was the delta we saw before charging. By the way, I found that the Model S packs are about 232 amp hour, roughly on their as a module.
15 amps is nothing in terms of
pushing
too much energy in too fast.
It'll take way more than that. So Sarah, so I hope we didn't, give you too much of like a long answer. I think it's a good.
Thank you, Richard, Ron, tell everybody. It's great.
And it's not to make it more confusing. I mean, if in summary, voltage might not tell you capacity. It's a good indicator, but it's not. And it's got to be under stress. In the interest of time, we should probably end the episode. But I think we're onto something here. The CAD files, the sharing of ideas. I mean, I think that the EV community meeting podcast thing that we're doing, this is episode 3. and we're already digging in deep here. This is pretty cool. I mean, any problem that someone comes across, you know, how trivial or small or big, it's going to be something that someone's thinking of. Like, how do you package your vehicle? You know, a lot of these electric vehicle classes, they always talk about, oh, how do you do the wiring? But how do you package your vehicle? So the CAD files, where do you place it, your gearing, stuff like that. And then what do you do about putty, which to me sounds ridiculous. Being not a computer guy originally, you know, like, I mean, I used to call it silly putty when we were talking about it out in California, you know, last summer. I'm like, this is absurd. Why do they call it putty? But I'm sure Richard knows, but anyway, so, but to me, it's like, it's absurd, you know, like it shouldn't be this difficult. Let's decode, let's bring all this stuff to the surface. So Sarah, write down your questions and let's bring all this stuff to the forward, because it shouldn't be this hard. Yeah.
And then also Sarah was there for the, you know, to kind of talk about upcoming things. You were there for that class with Lou over the summer, which we have at the EVLC coming up again, 27th from 10 to 4 at the EVLC. So if you're in Southern California or near San Diego, San Marcos area, you want to, it's now open to adults. That's the big thing, is that, you know, it's kind of a kids class, and Sarah was there as a teacher, you know, learning as a teacher there. But after popular demand, the class for the battery building is going to be now open to adults as well. So again, January 27th from 10 to 4 at the EVLC, right across the way from the EV West office.
Yeah, and you know, Lou is great. He's a great teacher. He was working on battery management systems like when lithium first came out, so years ago, and even before lithium, working on NiCad batteries. So he knows a thing or two. Plus, he's a cool dude. He plays bluegrass music. He's a real nice guy. They call him Abuelo, which I guess is, I don't know if I'm pronouncing it right, but he's like the grandpa, you know, of batteries. And so you really should take a class with him. Anybody listening to this. Cool. That was a perfect segue, Talik. I almost forgot about what a good class that is. Nice one. Okay.
Well, Sarah can talk about it because Sarah was there.
Yeah. Sarah, you took his class. Did you do something with Lou?
Yeah, actually, I volunteered to help teach it to the kids.
Perfect.
So, but I did it, you know, selfishly so that I could learn. And I learned a little. But yeah, spot welding. I'd never done that before. That was cool. Yeah.
Oh, you just described my whole career. I teach because I just like doing stuff and learning.
Well, maybe you do have the skills to go in there and fix that module if you have a bad cell.
I would love to investigate that. Yeah. I mean, no, I don't want to investigate that, but yeah.
Don't forget, you're in Northern California, is that right?
I'm in Joshua Tree.
Is that far from LA?
2 hours.
It's east of LA.
Don't forget, you got Jehu Garcia in Rancho Cucamonga.
Yeah.
Cucamonga. And he is like deep battery guy. I think he has a real good understanding because he did so many packs that were handmade. You know, and that's something that, you know, like nobody wants to hear this, but you really should try and make your own little pack, at least a drill battery pack, and put a BMS on there and stress it out. See if you can get it to, you got to break, basically you got to learn through failure. You got to break something before you jump into all the big stuff. Because how are you going to know, you know, and me included, I didn't realize that you do have to stress that battery to find out the capacity. Otherwise, you know, that voltage thing is, it kind of tells you a little bit of the story, but not the whole story.
Mm-hmm.
All right. Well, this is great. Richard, I really appreciate you being here. I think you're a great resource.
Yeah, thanks. I learned a lot from you. Thanks for the 3D modeling. Give me some idea of what the capabilities are. You know, it's very cool.
You know, Richard,
you know, at the design stage, before you've even chosen what drive unit to use in your vehicle, will it fit?
Right. You know,
how big of a hammer do you need to make it fit?
yeah, exactly. You know, Richard, don't be afraid to reach out if you want me to. I'll try and put it in the chat before we leave. I could show you the basics of CAD. Not that you're gonna like make your own motors or anything, but you know, it's a good skill to have, and I think that a man of your capacity, you absolutely could learn this pretty quickly. And that goes for anyone. Honestly, I teach this to high school kids, and they pick it up like super quick. So I think you could do it.
Okay.
Cool.
Yeah, it's a matter of putting the time in and learning the terminology. And I'm still writing code in C here for an ECU for another EV project that's here in San Diego. So trying to fix bugs in C code.
Wow.
So that's what I know.
Yeah. And also, Tom is here. Tom, I don't know if he's still listening, but thanks for coming in. I know it's been we kind of went off on the thing about all these different batteries. Are you still there?
Yeah, no, this is very stimulating. I actually kept you on the whole time. I stopped at the post office to check my mail, and I also went to auto parts store and got a car cover. Yeah, you kept me company. I really appreciate the question from Richard and also Sarah. And I'm so glad that you threw in Jehu. Because he stresses bottom balancing and taking his when he's a distributor of batteries, but he's also a recipient of large shipments of batteries, and so whenever he gets a shipment, he demonstrates capacity and bottom balancing and taking it back up to the top before he ships. He doesn't do that to every battery that he ships, but he does it to each selected samples from each shipment that he gets, so that you have a general idea of what capacity is going to be. But he has a money back guarantee. If you get a bad cell, he'll make it right. So a lot of his videos are about just what we were talking about there with you and yeah, you guys kind of went in the weeds a little bit on that between Richard and Ron, but thank you so much, because it will ruin your day. And the part that you guys didn't mention was that, yeah, we got our batteries mixed up. We had a good set of batteries and we had a mystery set, and we just got them mixed up, and it was really nobody's fault, except, yeah, we didn't double check, did we?
No, and it's all good because they look exactly the same, you know?
Yeah, yeah.
But yeah, that's the thing is, not that you have to, check everything, but yeah, if you got a critical project, then yeah, I would. And honestly, it didn't take much time. We charged it for literally a minute, and one of the cells went to the roof in less than a minute, and that really showed us something going on. Anyway, in the chat, I put a really simple CAD lesson. I call it CAD lesson 1. I call it Tony Stark's Cyber Donut. It's a little ridiculous because it's for high school kids, but you might find it fun, and it's really simple to get you started. So, Richard, let me know if that thing jives with you, if it works.
Okay. Yeah. Thanks.
Okay. All right. So I'm going to stop the recording right here. And Talik, thank you. Talik's kind of like a co-host in a way. It seems like we'll just do these. Maybe we'll try and shoot for an hour. It looks like we went over the hour. We'll try and shoot for an hour, and I'll get a better connection. And Talik, I'm sorry, I'm volunteering you. You're going to be the co-host, because every week and the Shop Class podcast, I might not be able to do that. But I think that you have a good understanding. You're coming into the EV space with a lot of volunteer work. You've been at the EVLC a lot, so I really appreciate that. So there you go. Okay, so yeah, if you got a girlfriend, you're gonna lose her because you're gonna be busy doing this. So
that is so ironic.
Yeah, that's it. All right. Okay, so I'm gonna hit record, end recording. Thank you so much. Stop recording.
Thank you. Very useful.
Yes.